Good morning, ladies and gentlemen. And sorry, I still have my first coffee. Today we talk about probabilities, and we will try to understand simply, to touch with our hands, a probability of, for example, tossing a coin or rolling a die. Okay, I conveniently added a couple of graphs here to make things simple for you. So number one, probability usually it's simply defined as the number of the probability of an event, let's say of E, is the number of positive events divided by the number of possibilities. Let me give you an example. The probability of tossing a 1 is the number of ones you get over a toss of a die, which is 1, over 6, which is the number of faces. This is under the assumption that this is this is not a tricky die, like this is a normal die. So 1 is equiprobable to 2, which is equiprobable to 3, and so on until 6, right? So probability is usually, there are different schools, but usually is defined as the number of positive events divided by all the possible events. What is the probability of the die giving an even number? Well, is the cardinality of the set 2, 4, 6 divided by the cardinality of the whole set 1, 2, 3, 4, 5, 6, which is 3 divided by 6, which is 50%. And the inventor of evenness rests happy in his tomb, right? So now let's get juicy, right? So let's get into rolling a die. This is a die, okay? One thing that is very interesting when you do probabilities is to create a map of probabilities, it's called density of probability, and it's a graph of all the possibilities multiplied by their probability. Okay, for example, what is the probability of dying of COVID due to your age? So you would have probability of dying of COVID here and your age here in years. So I would presume that after 120 years it's 0 because nobody is that old, and it starts with 0. What is the probability of 0? It's probably low, 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 low. When you get to 40 or to 50, it gets a bit higher, then it gets higher, and then it gets a bit lower maybe, or always gets higher. I don't know, I'm ignorant. One important thing is that the area of this mountain is 1, because probabilities are always the sum of all the events, provided that all the events sum up to all the possibilities on the planet, it is 1. This is by construction, because that's when the number of positive events equals the number of possible events. So is tomorrow another day? Yes, 100%. Is tomorrow raining? 27%. Is tomorrow not raining? 73%. But the sum of raining and not raining is 100%. And 100% is 1. Remember, 100% is for a human being. It's like a easy peasy talking. But in math, 100% is 1. 1. Difficult to think, but 1 is 100%. Okay? Now, this is the map of probability based on a certain grandeur, which could be, I don't know, in this case it was age. In the case of a number, let's take all the possibilities, 1, 2, 3, 4, 5, 6. Each of them has 1/6 of possibility. So in the case of rolling a die, the map of probability is 6 points, which are 1/6 tall, so 0.1666666. And there are 6 points here, and all the other are 0. What is the probability of getting a 7? 0. Of getting 42? Unfortunately, also 0. I wish it could give a 42, but you cannot. You could have this, still you couldn't have a 32, but you can have a 28, as you can see, because this is a 30-sided die, right? You have the number 20. If you play Dungeons and Dragons, this is one of the most famous, right? The icosaedron, or whatever you call it in English. Now let's get to the number 2. Let's get now to the incredible part, the part that most people fail to understand, which is what happens if you combine probabilities? What happens if I roll 2 dice? So let's say I roll 2 dice. The possibilities are 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. And let's say that I take the sum of this. And let's call it, in Dungeons and Dragons, this is called 2d6. A 2d6 has a number of possible, so that you can have from 1, 1 to 6, 1 and to 6, 6. So you have 36 possible die roll. 6, and for each one of the 6, you have 6 here. Note that this is the probabilities, sorry, the different possibilities are 36 of rolling 2 dice. If you had a bag with 6 things, number 1, 2, 3, 4, 5, 6, and you removed 1 each, then the probability would be 6, the possibilities would be, 6 for the first, but then you remove, let's say you remove the number 3, then in the bag you only have 1, 2, 4, 5, 6, and then you have only 5 possibilities. So that's a different branch of probability, which is the getting out without putting back in, okay? It's a different kind of math. But in rolling 2 dice, thinking that it's very important thinking that the first die you roll is completely independent from the second. So whatever happened to the first doesn't have an impact on the second. So this means an unconditional probability, okay? In this case, you have a map of possibilities which are here. So what is the sum? Well, the sum will go from something like 2 to something like 12. Now, since I had a fight with the professor, father of my best friend when I was a young kid, I can tell you, and this I don't say in Italian, I can tell you this, at first you could say, oh, but throwing a 2d6 is like throwing an 11 die, rolling an 11 die and add 1. If you think about it, if you throw an 11 die, is a number from 1 to 11, and you say, but there is no such thing as a die with 11. Yes, but have you heard of computers? You can always randomize a number from 1 to 11. So this also goes from 2 to 12. But I want to show you that the spectrum, or if you do a CAT or X-rays to this die and to this die, you will obtain a different spectrum. That means you have different probabilities. And this is the first thing that probably human beings don't see unless they're mathematicians, but it's important. So let's try to digress into these 2 die. So if you roll 1 and 1, it makes 2. 2 and 2 makes 4. 2 and 1 makes 3. 1 and 2 makes 3. So like, wait a second, why 1 and 2 and 2 and 1? Aren't they the same thing? Great question. No, they are not. Rolling 1 on the first and 2 on the second is different from rolling 2 on the first and 1 on the second. If your first kid is a son and your second kid is a daughter, you can bet it's different from your first kid to be a daughter and your second to be a son, right? You wouldn't probably be able to map that, right? So you might have a son and a daughter, but it's important that the oldest is a son and the younger is a daughter, or vice versa. If you just want to count the genders, you can say 1 and 1. But in probability, it's important to label each event, and even artificially say this is the first event, this is the second, because of course I don't care about the first and the second when I do a sum, but it's important for mapping. And if you don't do that, you will get wrong numbers. So please do it. So once again, if I do 6 and 6, I get 12, 6 and 5, I get 11, 5 and 6, I get 11. So that tells you already something very interesting, that to get a 2, you need to roll 1, 1, which is one probability. The probability of a 2, to getting a 2, is 1 on 36. And the same is probability for 12, because they're mirror, they're specular. Okay, but the probability of a 3 is not 1/36, it's actually 2. Because think about it, like, to get a 3, if your life depends on getting a 3, you know that the first die, if you roll a 3, 4, 5, 6, you're dead. But if you roll a 1, there's a chance that you get a 2. If you roll a 2, there's a chance you get a 1. So you see, you have 2 possibilities out of 36. I don't know. Now that your life is on the line, you see that. And 7, oh my God, 7 is amazing. You can do 1, 6, 2, 5, 3, 4, 4, 3, etc. So you have actually, the probability of a 7 is the most likely. It's 6 over 36. In percentages, because that's a bit easier, this is roughly 3%, and this is roughly 17%. So it's a lot of difference. If somebody points a gun to your head and say you're going to about rolling 2 dice, decide the number, and if you get the right number, you die. You don't die. Actually, every intelligent person would bet on the 7. It's still very likely you will die. 83% you will die, but you have a 17% of survival. Here you have 3% of survival. Better 17 to 3%, I hope. So this is the first kind of like unusual aspect of probability, which means when you combine different probabilities, the shape of the combined probabilities is not as it might look. So if you thrill, when I play Dungeons and Dragons, you roll 3d6 for intelligence, so you get a number from 3 to 18. You would think, oh, what is the probability of getting 18? To be the most intelligent person on the word of Crane, for example, is 1 on 216. So it's 0 dot, this is a 6 at the third power, to the third power. So it's like 0.5%. But the probability of a 10 or 11, now you need to use a the binomial formula, but it gets something much bigger, because it's like on a cube. It's similar to this, but it's tridimensional. The number of things that amount to 10 are 1 impossible, so 136, 145, 154, 163, 2 1 impossible, 226, 23. So if you count them all, let's try 145. 1, no, this is 10. 136 multiplied by 2. Then you have 2, 2, 6, 2, 3, 5, 2, 4, 4. These are multiplied by 2. So there's already 2, 2, 2, 2, 1. It's already 9 possibilities, and we're growing. With a 3, you have 3, 1, 6, 3, 2, 5, 3, 3, 4, 3, 4, 3, and these are multiplied by 2, and so on and so forth. You see, there are probably like 20 different combinations that gives you a 10, but only one that gives you a 3. I hope I convinced you, right? So now let's look at the spectrum, right? So the spectrum of rolling one die is this very trivial line. It's 6 dots. Now the spectrum of 2 dice is actually this. Is like a triangle or the pyramid of Michelino, if you want. Okay, it starts at 2 with 1 over 36. This is 1 divided by 36, and this is equally 1 divided by 36, and the climax is 1 divided by 6, or 6 over 36. So this is 6 times taller than the first, and then it goes back down. So 7 is the most likely number. If you roll 3 die, you get something. I think it's like 3 pieces of parabola patched together like a Frankenstein. And if you roll an infinite number of dice, let's say 20 d6 for a fireball, if you're like a big powerful magic user, it will converge to a Gauss curve, to a Gauss bell. I don't know if you pronounce it Gauss or Gauss, but you know, the famous bell with mu and sigma. Okay, so if you go to infinite d6, the probability map is something like this, which has a medium and inertia radius. Okay, and now let's get to the second part, like the mathematical. When you have a generic probability map like this, and let's say that there is a fundamental theorem of calculus that tells you that the convolution of an infinite number of distribution always converges to a Gauss bell, and the demonstration is pretty esoterical. I wouldn't be able to do that, but it is actually true. So that means that if you are in a class and you ask every student to give you a random distribution, 1d6, 1d7, 1d20, probability of dying from COVID, probability of dying from I don't know, smallpox by age, probability of dying killed by a bus by, I don't know, neighborhood in New York and stuff like that. All these distributions are completely different, but if you put them together, you sum them, or in Mathematica you would say that you use the convolution of two functions, f and g, means if this is f and this is g, the convolution is the integral over all of r of f of t g of tau minus t in the t. Or maybe it would be nicer if we want to keep t to revert t and tau. So it would be f of whatever, let's say tau, of g of t minus tau in the tau. This means that you're basically doing an x-ray of the two functions, multiply one by the other. So it's like if the functions are like ones and zeros, it's basically a selector in which you reverse one of the two and then you shift them, and the delta between the center of the two of them is actually t. So this is a function, let's say h of t, where depending on this t, you are doing the integral of, let's say that the first is this and the second is this, okay? This in zero, the convolution in zero will be exactly this integral, which will be, I don't know, here will be tall, but here is very small. Here it will be small, so it will be like, meh, it will be something like, I don't know, like here. But when you get here, you have a kind of like, in this point, it's probably a bit higher. In this problem, it's probably a bit higher. And in this point, in the middle, you probably have the maximum, something like this. Okay, and actually, when the delta is this, okay, let's call it I don't know, delta. Where you are in delta, in this point, you are basically doing the integral of this and this, which have the same peak. So here you will have the peak. I don't know, it's not very easy to visualize. Something which is much easier to visualize is in the case of a 1d6. If you do the integral, this is basically a rectangle. Think of a die, okay? This is a rectangle, and the second is also a rectangle, is the same rectangle. So the convolution will be something that you take the first and you reverse it. In zero, they are basically, well, actually the rectangle is probably centered in here, right? It's probably something like this. So the rectangle, sorry, let me do it better. The rectangle to be peaky should be probably centered in the center of gravity. So it will be something like this. So if you integrate in the center here, it would be this that selects this. So you have a maximum. But if there is a discrepancy here, basically this selects only this part. Of course, think of, I don't know, if you need to integrate this with this, the integral is zero, because here is always zero. Here is not zero, but here is zero, and zero by something else is always zero. So 0, 0, 0, 0, 0, 0, 0, until the delta becomes lower than this. At this point, the integral from zero starts to grow up linearly and reaches the climax when they are exactly like this. Here you have the maximum, and then you go back. So it's a triangle, exactly what I showed you here. If you convolve a triangle with a rectangle, you will obtain something that goes up like a parabol, because it's second degree. Then the parabol will go down in speed, and then it goes like this, and then it goes like this. So it's like 4 pieces of parabol, probably 3, because this is probably the same parabol. And when it converts to infinitum, you have this. So the formula will be e exponential lambda t by alpha, where lambda changes depending if this is as fat as Riccardo or as slim as something else, right? So how this is how the flex is far away from the center, and alpha is uniquely determined by the fact that the integral needs to give 1, because the sum of all the probabilities needs to be 100%. Remember? Okay. So that was kind of like the most things I wanted to say about probabilities. A little thing about conditional probabilities, just because I don't know in your country, but in Italy, a lot of people give you fake news about the fact that in these kind of online games where you, I don't know, like bingo and stuff like that, where in Italy we have lotto, where there is a number, and if you get the right number, you get a lot of money, and the number goes from 1 to 90, and somebody tells you, you need to play 31 because 31 didn't go out for 50 weeks. So it's very likely that today the 31 is coming out. Now that is complete bullshit. And this has to do with conditional probability. And let me explain it to you without talking about games, talking about kids. I wanted a daughter, right? And so when I had my first kids, I'm like, oh my God, I want a daughter, I want a daughter, I want a daughter. This probably, What is the probability of having a male or a female? Well, it's very close to 50% and 50%. Actually, it's not exactly like that. It looks like Mother Nature gives us a little bit more females, probably intelligently so since they host kids. So it's more like 51 and 49. But let's keep it easy. Let's say 50-50. So what is the probability of getting the daughter I want? 50%. To getting the son that I'm learning to love 100%, as you can see from my videos on YouTube, yes, of course, another 50%, right? Now, some people, what is the probability of having a male, 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 female, female, female? So this is of course 25% or 1/4. This is of course 1/4. This, as I said before, it's 50% because the probability of having male and female or female and male is each one of them is 25%. So 25 and 25 is 50%. So this is actually one possibility, and two possibility, right? So you could argue, since I had a male, the probability that the second kid will be a female, how much is that? Is that 50% or no? And now this is the point. Like, if you already know that your firstborn is a boy, the probability of having the second-born, we call it SB, second-born, it's still 50-50. And this is something that, I don't know, my mom and most people get wrong. Like, this is something 90% of people get wrong. Because it's slightly counterintuitive, but it is the truth. So, the probability of having male or female on your second kid, based on the fact that the first kid is a male, is still 50-50. Based on the fact that the first kid is a female, is still 50-50. Meaning the gender of the first kid doesn't influence the gender of the second kid. You could say, oh, but the probability of having 1 and 1 is 50%. So I know that you have a male, so you are here, and you have a 75% probability of having at least one male. And the probability, so one could argue that in the male spectrum, okay, this is female, since the firstborn is a male, I have 2 possibility out of 3 that the second is a female. I say, yes, that's true, but only if you don't know the first gender. So if you say, I don't know the first kid, what is the probability that the one of the 2 will be a boy is 75%, but I already know I had a boy. What is the gender of my second kid? It's 50-50. Right, so it's 50-50 versus 33-66. Most people will say 33-66, even people who are good at math, right? But that is absolutely wrong. And this is based on the concept of conditional probability. So it's very important when you try to combine events, like when I talked about convolution and this, that you know if there is orthogonality between the events. So event E1, the first roll of die, or E2, the second roll of die, or E1, my gender of the first kid, E2, gender of the second kid, the 2 probabilities are either orthogonal or not. If they're orthogonal, you can just use math to do them. If they're not orthogonal, you need to bias the second event of the first, meaning that usually you label the first and the second as it's convenient to you. And then you say the first event does whatever he wants by definition. The second, we calculate the second event based on the knowledge of the first. So you do a diagram like this. The first event is 1, 2, 3, 4, 5, 6. And for each one of these possibilities, we do a tree of possibilities for event number 2, which is, oh, it could be female or male, it could be female or male, or it could be whatever, right? And if they're independent, you calculate them independently, and math helps you a lot to merge them together with convolution. But if they're not independent, you need to go into this sad valley of tears, as we learned from the Big Lebowski, right? So this is a much more complicated thing. It could be the probability of dying of lung cancer if you're a smoker or not. Are they related, dying from lung cancer and being a smoker? Fuck yeah, it is related. If you smoke, you have, I don't know, 1 probability out of 6 of dying, like you have like 15-20% of dying. If you don't smoke, you have like, I don't know, 1% or 3% of dying. So there's an order of magnitude of difference between the two. God, yeah, there is a difference between the two, and it would be stupid not to use that knowledge. So usually it will be, if smoker, if non-smoker, and if smoker you die this, and if non-smoker you die this, if smoker that, and then you have like 4 possibilities. And then when you calculate the probability of dying, you take those 2 probabilities, you sum apples with apples, bananas with bananas, and then the probability of an apple, which is, I don't know, dying, divided by apples plus bananas, and then you get maybe, I don't know, 10%, right? Which is the probability of dying of lung cancer overall. I don't know, I hope that was useful. Just a couple of things. If the last part was important, was interesting to you, you might want to check out the theorem of Bayes, B-A-Y-E-S. And let me suggest to you on the gender of the kids, look at the problem of Monty Hall. Monty Hall is a beautiful kind of pseudo paradox based on a real case game that somebody invented in US in the 70s, I think, which is that there you have 3 doors. What is the probability of getting you can get, there are 2 goats and a car. You of course want the car. You have a 33% of getting the car, and after you chose the door, the presenter, the anchorman, opens another door, shows you a sheep and tells you, should you change your choice? A beautiful, beautiful, beautiful example where you see actually conditional probabilities in a game, so in a funny way. Hope that was useful. See you everybody. Have a good day.